centroid. Okay, so this over here is our centroid. Again, determine through observation, or we can do a calculation for it. So now when we have this, so this is our stress X, and stress X is based on Px over A. And then when we draw our Y, okay, so this is our Y-axis again. So the stress distribution, the normal stress distribution is going to be in this direction. Okay, so at this point over here, this is our Px over A. Okay, and then next we're going to do our bending moment. Let's sketch our bending moment stress distribution, where stress X is equal to minus mz over izz multiplied by y. So we will sketch this. Okay. So this is our stress X. This is our Y. And looking at over here how the bending. So now we're going to apply what I've taught you. Okay. So now this is the moment vector. All right. So moment about Z. So this will be compression. Over here on top will be tensile. Okay. So alpha, the top will be tensile, bottom will be compression. So we will have a diagram that looks like that. Okay. So this is our stress distribution. Okay. Okay. So now to sketch your stress distribution, I'll do it. So tensile means it's pulling away. The arrow will be pulling away from y-axis, and then the other one is compression, is pushing towards the y-axis. Okay. For this side, for the axial loading, is all pulling away. It's all pulling away. Okay. So now, when we combine the both of them, right? Let me see. I have enough space here. I'm going to squeeze some of these burgers over here. So when you combine the both of them, in the case for in the case for eccentric loading, now the stress will look like this. Okay, the resultant stress will look like this. So this is where the centroid is. Okay. So this will be our stress X, and this will be Y. Now we're going to plot stress X is equal to Px over A, right? Plus or minus mz over izz multiplied by y. Okay, because we have the normal stress. Okay, sorry, we have an axial loading over here. Because so now we are going to add these two graphs together. Okay, and this is the outcome. So the slope will still be the same. Okay, so just going to paste a slope. The slope is still the same, but you have a shift. Okay, you have the shift. So the shift looks like this now. Okay. So what you realize now, if we were to sketch the normal stress distribution, so this will be tensile, 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 and then this will be compression, compression, compression. Okay. Now this line over here that we see is still our centroid. No dispute. Now the position of the neutral axis have been shifted. So this is the shift of the neutral axis. Where did it shift to? It shift to here. So this is our neutral axis. Okay. So in this case, the centroid and the neutral axis are not at the same point at all. Okay, are not at the same location at all, right? So this is the difference that where you see eccentric symmetrical bending, and then the previous one that you see is centric. Okay, so for centric, the neutral axis and the centroid are at the same location, whereas eccentric, it is not the same. Okay, any questions so far?
Did you know for the windows did how did you know the top part was in tension? The
So if you
bottom was
look
in
the
compression.
how it's bending, we look at the bending vector, right? The head is in compression, the tail end is in tensile. Samuel, is that okay?
Yes.
Okay, right. So this is our difference between eccentric and centric. Now, the next one, I'm going to go into a bit on failure analysis now. Okay. At which point do we calculate where the failure will be? Okay. So we are going to look at identification of where failure will occur. Okay. So now we're going to look at a simply supported structure first. Okay. But before I go on, I would like to highlight this. Okay. What are the similar characteristic between simply supported and cantilever beam? Okay. So I'll elaborate on failure. Okay. By looking at the similarity with the simply supported and cantilever beam. So we know that failure will occur at location at the location of maximum loading condition. Okay. So the trick is you have to be able to identify where the maximum loading condition is. Okay. So if we were to look at again simply supported beam, okay, we look at simply supported beam, right? So this is again simply supported, and we have a load on the center P. Okay. So this is our point A. We call this point C, and this is our point B. Okay. So we are aware, okay, we are aware that failure will occur at point C, like what I explained this morning. Okay. But why? Why failure will occur at point C. Right? Why failure will occur at point C? So if I were to put in or calculate my reaction forces, we know that the reaction AY over here, I do apologize, I should not be squeezing like this. I'll just move this. Okay, failure will occur at point C, right? So we know we have a AY down here. AY is equal to P over 2. And over here, we have a reaction BY is equal to P over 2. This is only true if distance from here to here is L over 2. And the distance from here to here is L over 2. Okay. Now, are you ever curious, okay, that when you analyze a structure like this, you need to analyze from A to C, yes or no? Right? When you do your calculation, you do not need to go from A to B, right? You need to do from A to C. So why is that? Okay, I'll show you why. Okay, so we are going to form equation. Okay, we're going to form equation of shear force and bending moment equation. We're going to form shear force and bending moment equation. Okay, so we're going to look at 0 x to L over 2. Okay, so we have our point A. Okay, so this is our point A. We have it as P over 2. And over here, this is our geometric datum. Okay, that is our geometric datum, right? So this is from 0 x to L over 2. This is between point A to point C. Okay, point A to point C. So the distance x, this is our x. And then we're going to make we're going to have Vx that's coming down. And Mx is going in the other direction. Okay. Now, any idea why this direction? Anyone? Why Vx is coming down, Mx is going anti-clockwise? Anyone? Any idea? Can you remember? I hear no answer. I'm worried now. This is because, okay, when we draw the direction this way, okay, we assume positive shear and positive bending moment. Okay, and this is only valid if the analysis is from what? Left to right. Okay, if you're going to do right to left, okay, I know there's a lot of revision down here, or some of you can remember, some of you cannot remember. Okay. If we are going to do from right to left, okay, the geometric datum, so this is our point A, this is our point C, and this is our point B. The geometric datum still stays, and this will be your X. Okay. Now, if we do our analysis, so analysis direction, okay, from right to left, so we still have P over 2 over here, right? So for this case, the positive shear and positive bending moment changes direction. Now it is what? V as a function of X is going up, M as a function of X is going clockwise. Okay, And this is because we are making the assumption of positive shear and positive bending moment. Okay. So for the one that we are drawing now, that I'm showing now, the one at the top, we are doing the analysis from left to right. The one at the bottom, we are doing analysis from right to left. Okay, from right to left. So you have to watch for this. Okay, the direction changes. And later on, probably in week 11, I'll show you why you need to know both ways. Okay. So from here, we look at the top diagram, which I'm circling now. Right, we look at the top diagram. We know that we are going to do static analysis. Okay, static analysis. So this is our transformation, X, Y, rotation in the Z. Okay, so we will have positive that's going up. Summation of forces in the Y direction is equal to 0. So we have P over 2